So, well, good afternoon, and thank you for sticking to the end. And today I'm going to tell you about the data processing. And if you try to build a house, but this house happens to be built on quicksand, then it doesn't matter how well designed your house is, it's probably going to fall apart, right? So similarly, for the computing systems, the general belief is that well-designed, well-verified applications are not good enough if the underlying systems are not good enough. So, in trustworthy computing, the buzzword is what we call whole stack verification, whole stack guarantees. And indeed, depends on what kind of stack in your mind. There are different ways you can draw such a computing stack. But the common thing here is about the data layer. And indeed, we are at this time where data processing is no longer novel or exotic at all. And so how to make the data processing layer as safe as possible, or providing high assurance to this layer, is indeed the focus of this talk. And indeed, this is a very large topic, so I'm going to have to narrow down and focus on one particular subfamily of data processing systems, that is the online data processing systems. Well, think about your database that's currently deployed on the cloud servers, for example. And in this case, what we are looking at is that the data processing engine is continuously receiving requests from the clients. These requests could either be a query or it could be an update, and then continuously return the requests back to the clients. So, the keyword here is the continuous, right? So, this is the picture. On the right is the client. You can see the 01, 02, 03 is like a sequence of operations you would like to be sent to this data processing server, which is on the left. We can also call it the backend. And then the R1, R2, R3 are the results that keeps coming back to the client. So, this talk is more on the formal side, all right? In the spirit of Splash, you can say. What we have come up is calculus, and this calculus has operational semantics that captures the essential behavior of online data processing. And indeed, the punchline is always about metatheory, right? So what kind of guarantees you provide? So this is, our goal is we prove some of the essential properties about this flavor of processing systems. And along the way, we find that this is actually quite subtle. So we actually have an additional type system to enforce to make some good behaviors to happen and avoid some bad behaviors, all right? And finally, the system is mechanized and is in conc. So let me start, and let me just answer you can say a Merriam-Webster question, right? What is online data processing? I have a 1980 database system. I'm going to just deploy it on the cloud server that is online, right? So literally, if you look up a dictionary, yes. But look, in the experimental system research community, nobody would label their system or paper as online unless it solves certain problems. Or in other words, what we're coming up with, or what we're focusing on, is not to come up with a database foundation that could have been done 30 years ago, for example. So what makes these systems very different? From an experimental perspective, any researcher in those system community, if they want to use this word, they have to be tackling these very performance-sensitive kind of settings in terms of latency, throughput, and so on and so forth. That's not the focus of this talk, but what is the essence here is that to develop or design an online data processing system, the optimization design is the design itself, all right? It's not just about the query returns you something that's correct. It's always about how to do this fast, for example. So that also tells you why we want to focus on this, right? Because optimization does comes with the lingering issues on, is this correct, right? Are you actually returning something that's expected? So now let me talk about what features that are essential for this type of systems. And indeed, these are what the DOM calculus, our calculus, is focusing on. And specifically, we're focusing on two families of features. The first one is what we call incremental operational processing. And in general, this means that the operation can be processed incrementally so that they don't have to be completed in one shot, and so that you can make room for processing another operation. And you'll hear more about this for the rest of the talk. And then there is another feature that's what we call temporal locality optimization. What this means is that if you have multiple operations to be submitted in close in time to each other, then something can be done to turn this multiple operations into some more optimized form for processing. So you might think IOP and TLO seems to be too random or disjoint features, but indeed they're unified by one philosophy. So in philosophy, people talk about individualism and the community, right? So you can say offline systems, or you can say traditional data processing systems, they mostly are focusing on individualism. So they try to make one query to be solved fast, for example. But for online systems, the focus has been shifted to this community-based kind of philosophy, right? IOP in the end is really about, well, I will make my processing incremental so that there'll be some CPU cycles for you, all right? And then the TLO in the end is about, well, then we're both trying to process something. Can we just bend it up together and do something that neither of us can do separately? All right, so I'm going to use an example here. This is a graph database example. And this, there are nodes and edges, right? So how to write this as a program should be relatively clear to you. Here, add is about node addition, and the add R is about the relationship addition. And well, how this works in a conventional semantics is fairly obvious. So I'm going to just quickly run through this animation. And I don't think I need to explain much. You see, nodes are added, and edges are added. All right. So now, what I really wanted to tell you is how IOP actually behaves a little differently. So if you have the same program here, but if you're subjecting to the incremental data processing, what you're seeing here is that, well, I'm going to just run the first half, reaching the halfway point here. All the nodes have been created, right? But let's just look at the last 5 lines, which is about the relationships. So I'm going to assume that these 5 nodes are going to be traversed from Eve and Deb and Cab and so on. So what is happening here is that when add R, the CB, this particular operation comes, the processing itself is actually asynchronous. In other words, it's not, the client is not waiting for it to end, and the control immediately goes to the next line, and the second operation at RDC might also be issued. And from this point on, these 2 operations are going to be processed in an incremental and non-deterministic propagation process. What that means is you can see this first one at RCB now it starts this process propagation, right, from Eve to Deb now. But before it finishes, now the second operation also starts its propagation. And as you can see, this is non-deterministic because you could have had the first one take another step, right? But instead, I'm having the second one to take another step. And so this is how this process is working here is, as you can see, you have multiple operations that might be processing at the same time, and the processing itself is incremental. So you can say why this is important, or why data processing system people love it. There are many reasons. I'm just putting some of these answers here.
Here's what I found.
Oh, I'm sorry. I don't know what's going on. This can allow some flavor of incremental query answering, for example. And also, it's good news for load balancing because, well, when I don't have CPU cycles, I don't have to finish myself to be processed. And this third bit is about a late arriving operation may actually gets to be finished earlier than the earlier arriving one. And you might think, why people do this? There's this family of problem called long tail. Sometimes because one operation gets so delayed that everything else gets delayed. And with this flavor of IOP, this problem is mitigated. So over here, you can see that's one possibility of execution that can enable this. You see, I'm actually having the later arriving operation to be completed first before the first one finishes its propagation. See? All right, so now let me talk about the TLO. So this is slightly easier to understand, and I'm gonna just change this program by adding one more expression statement to the end. So what I'm doing here is I'm adding a relationship between node A to node E, but then I immediately delete it. You might think this is strange, right? But in reality, there's actually these studies about social networks. Recently updated nodes are actually updated again very, very frequently. So this is actually a common pattern. So what is happening here is that with TLO, the data processing engine can actually find out that these two operations are related, okay? Instead of having each of them finishes processing, we can just say, well, look, you're adding something and then very quickly you're deleting it. So they can be canceled out on each other without taking the CPU cycles to processing either of them. And so the theme here really is that you wanted to optimize multiple operations before they are individually realized to avoid unnecessary work. And indeed, this canceling out, this is just one example. And the more general case we call it diffusion. So in other words, multiple operations can be combined. And that's not even the only one. You can also reorder different operations, assuming you do not change the results. And you can also have the earlier one to compute something that can be shared with the later one that we call reuse. Or finally, it's about a batching. This is actually very commonly used in data processing system. That is, multiple operations can be just batched together to go through one round trip. So now our calculus studies IOP and TLO in one, and this is actually not accidental. It actually leads to some of the interesting design spaces, I think not even existing in the existing systems. And that is, for example, fusion now can actually happen anywhere during the propagation. So in the early example, I showed you the add and delete can be canceled out when they're first submitted, right? But now they can already halfway propagated and then opportunistically cancel out each other during their propagation. Right. So from this point on, let me tell you about the calculus itself. So the add node and add relationship, those are all syntactic sugars. So what we end up having is a calculus with 3 primitives about the add, how to add a node. So in this case, add a node with a particular value to it. And then map is like a write, and fold is like a read. So the way to look at these expressions is that the first expression, the first argument for map is standard, that's your mapping function. But the second argument, you can actually specify a subset of nodes that each of them will be applied to this mapping function. Similarly, analogously to fold. And so we show that these primitives actually are sufficient to capture these common data processing operators you probably have in mind. And also, we do not explicitly model graph edges, but they can be part of the node value itself. So expressiveness-wise, it's the same. And finally, we do not have deletion because in real-world systems, node deletion is generally a marking to the node and then sweep later. So in that sense, the map would capture the essence of deletion. So the calculus has the support spanning the entire back end and the front end. And on the front end, we essentially have a future semantics that supports asynchronous processing. So you can say, well, the operation submission and claims are like future operations. And then on the right, on the left, this is where all the TLO and the IOP are happening. And so a key formal invention in this exploration is what we call operation streams. So what we realized is that when these operations keeps coming, what is very natural is to think about a stream of operations that are flowing through these data nodes. And so what this means is that now the runtime can just represent this piece of data as a sequence of what we call stations here. You can see the 5 stations for this example. And each station consists of nodes, which is the standard node information, right? But then there's also this second component that we call streamlet. So what this means is it's about the subset of operations that has reached my node now, okay? So you can imagine this whole stream is diced up into different streamlets, one for each node. And for example, this figure on the left is essentially maps to a runtime on the right, like this. And or here's another example. Now I don't have time to tell you everything about the semantics, right? So let me just tell you what is the essence of IOP. So the point here is IOP is never about process the entire operation by traversing all the nodes. Instead, it's really a local step that only involves 2 adjacent nodes. For example, if I would like to process this LR BE in this case, what I'm going to do is to take off the head of this earlier station, the streamlet in the earlier station, and append it to the tail of the next node's streamlet. All right. So, or I can write this like an instance of a reduction rule. All right. I'm not going to write out the rule, but I think everybody looking at this probably will figure out what the Greeks behind it. So, look, this head and the tail thing actually matters because even though we're doing this non-deterministic propagation, the chronological order of the processing is actually preserved. And if you look at the TLO, that is essentially to pick a streamlet and then apply some of the rewriting rule. This can be a fusion rewriting rule or batch rewriting rule, reordering rewriting rule, and for simplification. All right, or operationally, this is one example. All right, so now with a lot of the non-determinism comes into the picture, the challenge here is about correctness, right? So does this system provide deterministic results? And in other words, if we say optimization design is the design for online systems, then is there a soundness that all systems should preserve? So, well, as it turns out, it's not obvious. Let me show you this example here. What you're seeing here is that there's a map that's being, essentially you want to update the node of camp, okay? And upon updating the node of camp, you're going to issue another map. In this case, it's going to update the node of Amy. And followed that is another update of the Amy itself. So the problem here is that depending on this inner map in the third line is executed first or finished first, or this last map is completed first, you might either in the end get the Amy's payload to be either 1 times 2 plus 1 or 1 plus 1 times 2. So there are actually different results, right? In other words, we're going to run into these non-deterministic situations. So if you look at the high-level insight behind this is like a race, right? So how do we get rid of this? We came up with a type and effect system. The property that we enforce is essentially phase distinction. So what we are saying here is that if the computation is going to happen on the front end, then it's non-restricted. But if it's happening on the back end, then we do not allow another operation to be issued. Okay. So with this, we can prove that the result is indeed deterministic. And this turns out is a non-trivial result because look, both IOP and the TLO are non-deterministic executions that can happen anywhere in this data itself, right? So to achieve determinism is actually not a trivial result. So for our calculus, we have mechanized it. And this is about 6,000 lines of code, mostly written by my student, Philip Dexter. So I'm just piggyback to present. But and the core of this really is a confluence proof, and it's in the flavor of the UAT confluence work. We think that this could also, the subcomponent could potentially be an independent artifact if you happen to be mechanize something on Confluence, for example. And there are some practical considerations I'm not going to tell you about. For example, how to support non-graph data, right? Like, what if it's a traditional relational database? Can you do this? The answer is yes. And then how to combine this with index access? The answer is yeah, there is a way to do it. And so to conclude, we believe that IoT and IOP and the TLO are the essence of online data processing, and the soundness of these optimizations are not trivial, but they can be established in cases when you're careful. And finally, we think that this mechanization can be a first step for semantic engineering in this critical application domain that if you are a experimental data processing researcher, potentially you can just build your own cock proof on top of ours instead of redo the 6,000 lines of code. So, all right, that's all for me. Questions? Yes.
Hi, because you skipped almost the last slide about practical application. So I'm just wondering, because calculus is pretty high-level abstraction. So I wonder, how the proposed model actually easily model the practical applications. I mean, from practitioner's viewpoint.
Right, how to model the like a graph processing operations? Is that the question?
Yeah, yeah.
Okay, so in the paper we showed, for example, one in some of the graph processing system like a Prego, right, or Giraffe, the typical operations are essentially about how to pull. That is, how the neighborhoods of your graph, the information from your neighborhood nodes can be used for computing something of yourself, or push. That is, I have something now, can I propagate it to my neighbors? And we have some encodings about how that is done. I mean, the essence here is that, look, map here is about right? And it's not just map write to one node. There is a parameter that says which node I would like to write to, right? Similarly, for fold, this is about getting something, a collection of nodes, and get some results back. So we have some encodings along those lines.
Okay, yeah, because I wonder there might be some bug, reported in real system, and
right.
proposing this calculus might help, fixing that kind of bug by practitioners. So, do you have any scenarios, or do you know any actual bug case?
So the one case that we put more work on is a system called Kickstarter. So it's an Ask Plus work, maybe 5 years back, and we essentially faithfully modeled all their metadata support and all their query support as well. It's not a complete system though, because for us we don't care about some of the details of their. For example, that's like approximation based query answering. So we did not study that part. But the hope is that it's only when you have a deterministic system to build your system on, you can talk about these other properties, right? So hopefully our theorem can be a lemma for them if they wanted to mechanize it.
Okay. Yeah. Thank you.
Sure.
Any other questions? Anything online? All right, then let's thank David again.
Yeah, thank you.